In the vast, warm waters of the Pacific, a monster is born. It is a spectacle of nature's raw power, a swirling vortex of wind and rain that can grow to dwarf entire countries. We call them tropical cyclones, but you might know them by their regional names: hurricanes, cyclones, and typhoons. Among these titans, however, there exists a more ferocious class, a designation reserved for the most powerful of them all, the super typhoon. So, what makes a typhoon super? The term is an unofficial but widely used classification from the U.S. Joint Typhoon Warning Center for storms that reach sustained wind speeds of at least 150 miles per hour, or 240 kilometers per hour. To put that into perspective, this is the equivalent of a strong Category 4 or a full-blown Category 5 hurricane on the Saffir-Simpson scale, the highest ratings possible. These are not just strong winds. These are forces capable of causing catastrophic failure to buildings, ripping roofs off well-built homes, and turning everyday objects into deadly projectiles. And they are born from a precise and powerful recipe of oceanic and atmospheric conditions. Think of a super typhoon as a colossal heat engine, a machine that runs on the planet's own warmth. Its fuel is the warm, moist air over tropical waters. The process begins with a pre-existing weather disturbance over an ocean with a surface temperature of at least 26.5 degrees Celsius or 80 degrees Fahrenheit. And this warmth can't just be a thin layer on the surface. It has to extend down at least 50 meters deep. This deep pool of warm water is the fuel tank. The water evaporates, rises, and creates an area of lower pressure near the surface. As that warm, moist air continues to rise, it cools and condenses, releasing a tremendous amount of what scientists call latent heat. This released heat warms the air column, making it lighter and causing it to rise even faster, which in turn draws more moist air in from the surface like a massive atmospheric vacuum cleaner. It's a self-sustaining cycle of raw power. But warm water alone isn't enough. You need spin. This is where the Earth's rotation comes into play, creating a phenomenon known as the Coriolis force. This force gives the developing storm its signature rotation, causing the inflowing air to spiral counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. This is also the reason these massive storms rarely form within 5 degrees of the equator. The Coriolis effect is simply too weak there to get the spin started. The final crucial ingredient is a stable atmosphere. The storm needs an environment with low vertical wind shear. That means there's very little change in wind speed and direction as you go up in altitude. If you have high wind shear, with winds blowing at different speeds or directions at different heights, it acts like a brake, tearing the storm's delicate vertically stacked structure apart and preventing it from organizing and strengthening. When all these conditions align perfectly, a deep, warm ocean, enough spin from the Coriolis force, and low wind shear, a humble tropical disturbance can explode in power, growing into a tropical storm, then a typhoon, and, if it remains over its energy source long enough, into a terrifying super typhoon. The vast expanse of the western Pacific Ocean, often called Typhoon Alley, provides this ideal breeding ground more frequently than anywhere else, making it the most active basin for tropical cyclones on the planet. Now, you've probably heard the terms hurricane, typhoon, and cyclone and wondered what the real difference is. The answer is surprisingly simple. It's just geography. They are all the exact same weather phenomenon, a tropical cyclone. If it forms in the North Atlantic, the central North Pacific, or the eastern North Pacific, we call it a hurricane. If it develops in the Northwest Pacific, it's a typhoon, and in the South Pacific and Indian Ocean, it's known as a cyclone. Different regions also use different scales to measure their intensity. While the U.S. uses the Saffir-Simpson scale from Category 1 to 5, meteorological agencies in Japan or the Philippines have their own classifications, like very strong or violent. But whether it's called a Category 5 major hurricane or a violent super typhoon, the underlying message is always one of extreme, life-threatening danger. So, what does one of these storms actually look like if you could dissect it? To understand the destruction, you have to understand its anatomy. At the very heart of a mature, powerful super typhoon lies the eye. It's a deceptively calm and often clear area at the storm's center of rotation, ranging from just a few miles to over 40 miles wide. Inside the eye, the winds are light. The sky might even be blue. This eerie tranquility is created by air from the upper levels of the storm sinking into the center. But this calm is a cruel deception because it is surrounded by the single most violent part of the storm, the eye wall. The eye wall is a towering ring of dense, violent thunderstorms that contains the typhoon's most ferocious winds and heaviest rainfall. This is the zone where the storm's power is most brutally concentrated. Air spirals inward toward the center, shoots upward in the eye wall with incredible force, and then flows out at the top of the storm. For communities on the ground, the passage of the eye wall marks the absolute peak of the storm's fury, a terrifying roar, accompanied by a horizontal barrage of rain and debris. Extending outward from this violent core are the rain bands, the long, spiral arms of clouds and thunderstorms that can stretch for hundreds of miles. These bands bring their own gusty winds and heavy rain, and can even spawn tornadoes, extending the storm's destructive reach well beyond its core. The sheer size of these storms can be difficult to comprehend. The largest tropical cyclone ever recorded, Typhoon Tip in 1979, was a true monster. It grew to a size that remains unmatched, with a diameter of gale-force winds stretching an astonishing 220 kilometers, or 380 miles. That's nearly half the width of the contiguous United States. And when a storm of this magnitude makes landfall, it unleashes its three primary hazards. First, the extreme winds we've discussed, capable of obliterating structures. Second, the torrential rainfall, which can dump staggering amounts of water, leading to catastrophic floods and deadly landslides, especially in mountainous regions. But often the deadliest threat of all is the storm surge. It's crucial to understand that this is not a tsunami, which is caused by seismic activity. Storm surge is an abnormal rise of water generated by a storm's powerful winds, pushing the ocean surface toward the coast. This creates a dome of water that crashes ashore, flooding areas that are normally high and dry. It's not a gentle rise, but a wall of water that can surge miles inland, a battering ram of the sea that destroys everything in its path. The history of the Western Pacific is punctuated by the passage of these monstrous storms. Perhaps no event illustrates the modern-day horror of a super typhoon better than Haiyan, known in the Philippines as Yolanda. On November 8, 2013, Haiyan made landfall in the central Philippines as one of the most powerful landfalling tropical cyclones in recorded history. The Joint Typhoon Warning Center estimated its 1-minute sustained winds at an almost unbelievable 195 miles per hour, or 315 kilometers per hour, at the moment it hit land. What followed was a near-apocalyptic scenario. The city of Tacloban was virtually wiped off the map. It wasn't just the wind that did it. It was a storm surge that behaved like a tsunami, a wall of water that swept through the low-lying coastal city with incredible force. Eyewitnesses described the sea rising in minutes, swallowing entire communities. The final death toll exceeded 300 people, with thousands more missing. Millions were left homeless. Haiyan became a global symbol of the terrifying vulnerability of our coastal populations and a desperate rallying cry for climate action. And these events keep happening. In 2016, Super Typhoon Moranti presented a chilling spectacle on satellite imagery, a near-perfectly symmetrical storm with a tiny, sharp, pinhole eye, the very picture of a maximally intense cyclone. It also reached peak winds of 195 miles per hour before slamming into the Philippines and Taiwan. Then in 2020, Super Typhoon Goni, known as Rolly in the Philippines, intensified with frightening speed and made landfall in the same region as Haiyan, again with estimated winds of 195 miles per hour. It brought catastrophic winds and triggered lahars, violent mudflows of volcanic ash and rock from the slopes of the Mayon volcano, which buried entire villages. Given the stakes, how do we see these monsters coming? Accurate forecasting is our first and most important line of defense. The backbone of this effort is a global network of weather satellites in geostationary orbit, giving us a constant, real-time video feed of storms as they develop. But to truly understand what's happening inside, we have the quote-quote hurricane hunters. These are crews from the U.S. Air Force Reserve and NOAA who fly specially equipped rugged aircraft like the C-130 Hercules and the WP-3D Orion directly into the heart of the storm. It's an incredibly turbulent and dangerous mission that yields priceless, direct measurements. The planes deploy instruments called dropsondes, which are like weather stations in a tube. They're released from the aircraft and fall through the storm, transmitting data on pressure, temperature, humidity, and wind speed at every level of the atmosphere. This direct and remote data is all fed into our most powerful forecasting tools, numerical weather prediction models. These are incredibly complex computer programs running on some of the world's fastest supercomputers, using the laws of physics to simulate how the atmosphere and the storm will evolve. Forecasters look at an ensemble of different models to gauge the range of possibilities for the storm's track and intensity. Over the past few decades, our ability to forecast a storm's track, where it will go, has improved dramatically. The cone of uncertainty has steadily shrunk, giving emergency managers greater confidence in issuing watches and warnings. The great enduring challenge, however, is forecasting intensity. Specifically, a phenomenon called rapid intensification, where a tropical cyclone's maximum sustained winds increase by at least 35 miles per hour in a 24-hour period. A storm that was a manageable Category 1 can suddenly explode into a major Category 4 monster, leaving coastal communities with terrifyingly little time to prepare. The precise ingredients that trigger this are still a hot topic of research, but we know it involves a perfect storm of ideal ocean heat, a very stable atmosphere, and specific structural features within the cyclone itself. Improving the prediction of this explosive development is one of the highest priorities for the meteorological community today. And this brings us to the urgent and unavoidable question: what role is climate change playing in all of this? While attributing any single storm directly to climate change is complex, the scientific consensus is clear. A warming world is loading the dice in favor of more powerful and destructive storms. Super typhoons are heat engines, and we are warming their fuel source. Human-caused climate change is unequivocally warming the oceans. Over 90% of the extra heat trapped by our greenhouse gas emissions has been absorbed by the sea, providing a deeper and more extensive reservoir of high-octane fuel for developing storms. The Intergovernmental Panel on Climate Change, or IPCC, has concluded that it is likely that the global proportion of major, that's Category 3 to 5, tropical cyclones has increased over the last 4 decades. And they project that the peak wind speeds of the most intense storms will increase with continued warming. So while we may not necessarily see more storms in total, the ones that do form have a higher ceiling on their potential power. A warming atmosphere also holds more moisture, about 7% more for every degree Celsius of warming. When a typhoon forms in this moisture environment, it can wring out this extra water in the form of more intense rainfall, dramatically increasing the risk of freshwater flooding and deadly landslides. Finally, and perhaps most certainly, there's sea level rise. As global temperatures increase, glaciers and ice sheets melt, and the ocean water itself expands as it warms. This rising sea level provides a higher launchpad for storm surge. A surge that might have been manageable a century ago can now penetrate further inland and cause far more extensive damage. simply because the baseline sea level is higher. The combination of stronger winds, more extreme rainfall, and higher storm surge means that climate change is acting as a, quote, threat multiplier, taking an already dangerous natural hazard and making it significantly more destructive. For the tens of millions of people living in these typhoon-prone regions, this is not an abstract scientific debate. It is a recurring reality. So how do we live with this fury? We can't stop typhoons from forming, but we can take steps to mitigate their impact and build more resilient communities. This requires a multifaceted approach. It starts with robust early warning systems that translate complex meteorological data into clear, actionable advice that reaches every household and prompts people to evacuate or take shelter in time. It also requires a revolution in how we build. The devastation from storms like Haiyan has underscored the critical importance of strong building codes and infrastructure that can withstand extreme weather. This means stronger buildings, burying power lines to prevent widespread outages, and designing water systems that won't fail. It also means investing in both engineered coastal defenses, like seawalls, and green infrastructure, like restoring the mangrove forests and coral reefs that act as natural, self-repairing buffers against storm waves. Perhaps most critically, it involves smart land use planning, restricting new development in high-risk coastal zones and floodplains. Resilience is also a grassroots effort. Communities can organize evacuation drills and establish public shelters. And for individuals and families, preparedness is everything. Having a go bag with essential supplies like water, food, and important documents, knowing your evacuation zone and having a plan, and securing your home by boarding up windows. In a future where super typhoons may become more common, shifting our focus from post-disaster response to pre-disaster preparedness is not just a strategic choice, it is a matter of survival. The passage of a super typhoon's eye wall is not the end of the ordeal. It is the beginning of a long and arduous journey. The immediate aftermath is a scene of utter chaos and devastation. The first 72 hours are a critical period of search and rescue, of finding the injured and accounting for the missing, often with communication networks completely down. The humanitarian crisis unfolds rapidly, with survivors needing clean water, food, shelter, and medical care to prevent the outbreak of disease. The road to recovery is a marathon, not a sprint, and it can take years, even decades. It involves the monumental task of clearing debris, restoring power, and rebuilding economies. It must also include providing mental health and psychosocial support for the deep trauma that these events inflict. The goal now is to build back better, to not just reconstruct what was lost, but to use the opportunity to rebuild in a smarter, safer, and more resilient way. The story of the super typhoon is a dramatic, ongoing narrative of a planet in flux. It is a testament to the terrifying power of nature, but also to our own scientific ingenuity in understanding it. It's a stark reminder of the challenges posed by a changing climate, and a powerful call for human resilience, adaptation, and the enduring strength of the human spirit in the face of the rising winds. Thank you for listening to G Fun Facts Online.